Ladies and gentlemen, this video cast is about finding net forces and the resulting motion when you know the net force acting on an object. Stop it if you need to record the I can statements. First, let's talk a bit about force diagrams and how to do force diagrams for a complex kind of an object. So for this baseball player, we could do a force diagram for his hands holding onto the bat. We could do a force diagram for his belt around his waist. We could do a force diagram for all kinds of different things related to this guy. So we have to first specify the system that we're doing our force diagram for. For the problems I ask you to do, that system's going to be pretty obvious. It will be obvious. I'll tell you what you need to be doing the force diagram for. On this one, I'm just going to show you some of the ways that we could do it on this gentleman. So first, system A would be the hitter and the ground. That's a pretty obvious system. The second system, system B, is the hitter and his ball cap sitting on his head. Nothing else, just those two things. So if we look at system A, the hitter and the ground, then clearly the force due to gravity, or the weight, is going to be the combined weight of the batter, his clothes, his helmet, the bat he's holding, etc. So the player's weight and the combined stuff that he's holding, that's going to constitute the FG vector in this force diagram. And then there's going to be a normal force from each foot because he's going to put some of his weight on each of his feet. So here's the force diagram for the hitter on the ground. For the hitter and his cap, the FG vector is simply going to be the weight of the cap, because that's all we're paying attention to here is just the cap on his head. So the weight of the cap, that vector goes down, and there's a normal force, a support force from a solid surface that is supporting the cap, and so that creates the normal force straight up. So what are net forces, and what do we mean when we talk about net forces? Well, net forces are just the sum of all the forces that act on an object or a system that you've defined. We'll practice that a little bit, so that'll make a little bit more sense after we've done a few. One of the important things you see on the screen here is the notation that we'll use. So a capital F with a subscript NET can be used for net force, or we can use that kind of sideways looking M followed by a capital F. That sideways M is actually the Greek letter sigma, and in a math and science setting, that Greek letter sigma means the sum of. So in this case, it means the sum of the forces. There's some rules for combining forces. We need to establish directions for the vectors. So we typically do up and down as collinear vectors and side to side as collinear vectors. So if we did up and down, then we would call up positive most of the time and down negative most of the time. The second bullet on this page indicates that we can combine collinear vectors with addition. So we can combine an up vector and a down vector. We could combine a left and right vector, but we will never be combining this last one at an angle forces. We're never going to combine in our class an up vector with a side-to-side vector, a left or right vector. That's because that requires trigonometry, and most of us haven't done that yet. I feel quite confident that you could do that really well in a few years when you know a little bit about trigonometry, but we're not going to take that on in the 9th grade physics course. Okay, let's try this one. So this is a very simple force diagram. The force types are not identified here, simply the force magnitude. So we just have numbers that tell us how many newtons of force are applied in each direction. So for the up and down vectors, we can combine those up and down vectors because they're collinear. We have a down vector of 12 newtons, so that appears first in the equation as a negative 12. And an up vector of a positive 12 newtons, you add those up and you're going to get a net force up and down of 0. Similarly, if we look at the side-to-side forces, we're going to have a force of 2 newtons that's to the left, so that would be a negative 2 newtons, added to a positive 2 newton force to the right, and again we're going to get a net force side-to-side of 0. So in this case, the net force shown in this force diagram is 0, and the forces are said to be balanced. That's a very key term. When forces are balanced, you know that the sum of the forces is equal to 0. It's a key piece of vocabulary. Forces being balanced. Okay, so when we have balanced forces, then we know that the object is in a state of equilibrium. So when equilibrium just means that forces on an object are balanced. So these two equations you see on the screen are the same equation because F net and sum of the forces are just the same different notation for the same thing. The interesting thing about equilibrium is that knowing that an object is in equilibrium does not tell you whether or not it's at rest or moving at a constant velocity. You need to know more information about it to know what it's doing. Typically, you'll know what it's doing, whether it's at rest or moving at a constant velocity, based on information provided in the context of a problem. But you also need to know the names that we give for the two kinds of equilibrium. So the first one is static equilibrium. Static equilibrium means that the object is still, it's at rest. So think of that ST, static, ST, still. So something that's in static equilibrium is not moving, it's still. And all the forces acting on it are balanced. Its velocity is 0 and its acceleration is 0 as well. The next kind of equilibrium is dynamic equilibrium. And when an object is in dynamic equilibrium, it's moving at a constant velocity. And the forces acting on it are completely balanced. It's moving at a constant velocity. When an object has forces that are unbalanced, we call that disequilibrium. So an object that is in disequilibrium does not have balanced forces acting on it. When objects are in disequilibrium, they're not at rest, they're not moving at constant velocity, they are accelerating. And when an object is accelerating, the object will always accelerate in the direction of the net force. That's absolutely key. Objects always accelerate in the direction of the net force. Here's an example of a force diagram. We see the up and down forces are balanced. The side-to-side forces are not. There's a 2 Newton force to the right, nothing to balance it back to the left. So the net force on this force diagram is 2 newtons to the right. So this is clearly unbalanced. The object is in disequilibrium. And since the net force is to the right, this object would be accelerating toward the right. For these force diagrams all show balance. So all of these show objects that are in equilibrium. And based on what we talked about a moment ago about equilibrium, it's impossible to know without more information whether or not these objects shown by these force diagrams are at rest or moving at a constant velocity. We would have to read the context of the problem in order to make that determination of which kind of equilibrium they're in. Static equilibrium means the object would be still. Dynamic equilibrium would mean the object is moving at a constant velocity. Okay, thank you very much. I hope this helps a little bit. Do a great job on your homework.